Welcome to The Explainer. All right, today we're diving into this invisible force that powers pretty much everything. Our world, our technology, even our own thoughts. We're talking about the fascinating science of electrochemistry.
So let me ask you a question to get started. What do a car battery, an anti-rust coating on a ship, and get this, a single thought firing inside your brain all have in common? I mean, you've got massive technology, a simple protective layer, and this tiny biological signal. What on earth could possibly connect them?
Well, the answer to all of that is electrochemistry. It's this incredible field that looks at how chemical reactions can actually create electricity, and on the flip side, how we can use electricity to force chemical reactions to happen that wouldn't normally occur on their own.
Think of it like this. Electrochemistry basically has two different sides. Two personalities, almost like two sides of the same coin. On one side, you've got these spontaneous reactions that just want to happen. They naturally release energy, and we can cleverly capture that energy as electricity. That's a battery, plain and simple. But then, on the other side, we can use electricity as a tool. We can use it to force a chemical change to happen, like putting that shiny chrome finish on a car bumper. So it's this constant dance, this push and pull between chemistry creating electricity and electricity creating chemistry.
Okay, so let's start with that first personality. How in the world does chemistry create its own electric spark?
Well, the hero of this part of the story is something called a galvanic cell. Sometimes you'll hear it called a Voltaic cell. It's just the fancy technical name for any device that can take the energy from one of those spontaneous chemical reactions and turn it straight into electrical energy.
And to really understand how it works, we don't need to get all theoretical. Let's look at a real classic example that chemists have been using for, over 100 years now, the Daniell cell.
So what do we need to build one? It's actually way simpler than you might think. First, you need two different metals. In this case, we'll use zinc and copper. These are our electrodes. Then each of those metal strips gets dipped into a solution of its own salt. We call that an electrolyte. And the final piece of the puzzle is something called a salt bridge, which is just there to connect the two sides and complete the circuit.
Now, each one of these little setups, the zinc electrode sitting in its zinc solution and the copper in its copper solution, that's what chemists call a half cell. So really, a galvanic cell is nothing more than two different half cells hooked together. Okay, let's zoom in on the electrodes themselves, because this is where all the magic happens. Our two metals, the zinc and the copper, they each have a very different but totally crucial role to play. So the zinc electrode, we call that the anode. You can think of it as the giver in this relationship. It's where a process called oxidation takes place, and it literally gives away its electrons. That makes it the negative end of our battery. The copper electrode, on the other hand, is the cathode. It's the taker. This is where reduction happens, and it just eagerly gobbles up those electrons, making it the positive terminal. Let's follow one of these electrons on its little journey, okay? It starts at the anode, where a zinc atom says, "I'm out," gives up 2 electrons, and dissolves into the liquid. Those 2 electrons then zip through the wire connecting everything, all the way over to the cathode. There, a copper ion that's just been floating around in the solution grabs those 2 electrons and turns into a solid copper atom plating onto the electrode. And that's it. That directed flow of electrons, that is an electric current. All right, I know trying to keep anode, cathode, oxidation, and reduction straight can be a real headache, but chemists came up with a super helpful little trick. Just remember this phrase, an ox and a red cat. See, anode is oxidation, red cat, reduction is at the cathode. Super simple, and it works every time.
Okay, so we've established this natural flow, right? Electrons want to go from the zinc to the copper. But what if we decided to fight that? What if we tried to push back and force the current to go the other way?
Well, the key to that question is knowing the cell's natural strength. How much push does it have on its own? And for the Daniell cell, under standard conditions, it produces an electrical potential of exactly 1.1 volts. That's its natural, spontaneous power.
So that 1.1 volts, that is the magic number. It's the tipping point. If we apply an external voltage but it's less than 1.1 volts, our cell just overpowers it. It wins, and it keeps functioning like a normal battery. Now, if we apply exactly 1.1 volts, we get a perfect stalemate. Everything just stops. No current flows. But, and this is the cool part, if we push with more than 1.1 volts, we completely overwhelm the cell. We force the current to reverse. Electrons are now forced to go from the copper to the zinc. And just like that, our galvanic cell has become an electrolytic cell. We flip to the other side of the coin, and now we're using electricity to drive chemistry.
This whole thing brings up a really big question, though.
I mean, how do we even know these numbers? How does a chemist figure out that zinc has one potential and copper has another? Where are they getting these measurements from?
So here's the catch. You actually can't measure the potential of one half cell all by itself. It's impossible. It'd be like trying to measure the height of a mountain peak, but you have no sea level to measure from. You're just floating in space. You absolutely need a universal reference point to measure against.
So for any of this to work, chemists all around the world had to get together and agree on a universal baseline, an official sea level for electrode potentials that everyone would use, a single starting point.
And the solution was brilliant in its simplicity. They basically invented a sea level. They created a special reference half cell called the Standard Hydrogen Electrode, or SHE for short, and then they all just agreed. They agreed to define its electrical potential as exactly 0 volts, period. And just like that, they had the ultimate ruler to measure every other half cell against.
So now, with our 0-point ruler, we can finally see why our Daniell cell works the way it does. When you measure zinc against this standard, you find out it has a negative potential, negative 0.76 volts. And when you measure copper, it has a positive potential, positive 0.34 volts. Electrons always flow downhill, from the more negative value to the more positive value. And if you look at the total distance between them, the difference between negative 0.76 and positive 0.34, it's exactly 1.1 volts. It all clicks into place. Okay, so that's the nitty-gritty, the fundamental principles. Now let's zoom back out and talk about why any of this matters. Just how critical is this science to our world, from big industry all the way down to our own biology?
Honestly, the applications are just everywhere. That galvanic cell we talked about, that's what gives us batteries and fuel cells. But remember the other side of the coin? The electrolytic cell? That's how we produce pure metals like sodium or essential chemicals like chlorine gas. Those things require us to force a reaction using huge amounts of electricity. That's electrochemistry at work on a massive industrial scale. It's also the science that stops ships from rusting in the ocean and is at the heart of so many new energy-efficient and eco-friendly technologies.
But maybe the most mind-blowing application of all is the one that's happening inside you, right this second. It turns out that the transmission of every single signal from your senses to your brain, and all the communication zipping between your brain cells, it all has an electrochemical origin. That spark of chemistry we've been talking about, it isn't just in our batteries. It is, quite literally, the spark of life, the origin of consciousness itself.